Well, since it's about 4 o'clock, I guess it's about time to start the last presentation. My name is Bernie Thompson. I know I've met a lot of you before. I work on the partner engineering team here at Google with Chrome OS. And today I'm going to talk about a variety of sundries. So this is mainly a presentation covering a variety of gotchas and branching and build and all the stuff listed on this slide, basically, including sausage, which Dave will actually talk about. Okay. And if there are any questions, feel free to throw your hand up, and I'll try to at least stop and look every so often. And keep in mind, this presentation is not really the Getting Started guide. There actually is one at this link here. You may have seen it. It's very big and comprehensive, and will help get your development environment going and all that fun stuff. And of course, you probably have a Google contact. It may even be me, and we're glad to help you through any problems you might have getting going with Chrome OS. So the first thing we'll talk about here is repo and gerrit. So if you've started Chrome OS development at all, you may have seen the repo tool. No need to look at all these, lot of text here right now, but this is kind of a reference. Repo is basically what we use to get all your sources in place and keep them up to date. It actually came from Android, and it's basically a way of having a whole bunch of Git repositories managed at once, which is important because we have a whole lot of Git repositories in Chrome OS. And basically, if you were to start a new checkout, you would do a repo init. That kind of tells it where you're going to get your repository files from, and then repo sync actually brings them all down. And another one that you'll probably use commonly is repo upload if you don't want to use git push as a way of getting things onto the gerrit, which we'll talk about next. So how many people here have used gerrit before? Okay, a few. Good, good. Don't be scared of it. It's just a website. And basically what will happen is after you've made up a change, got it all prepared in Git, you use repo upload, and it will show up on this site here. The link's right there. This is actually the public side. Anybody can create an account on it, and anybody can put a change up on it. So I would encourage you to create an account and try to put up a change if you haven't done so, and you have any interest in developing on Chrome OS. And keep in mind, since Chrome OS is open source, or at least Chromium OS, all the major components are actually on here. So you can see almost everything going on by looking through this website, and you can contribute it to yourself, no matter where you're from. There is also an internal version for some of the repositories that we have to keep private. For things like new unreleased devices, we normally have a private overlay and that type of thing. It's basically the same thing, just with a different color and with pointing at some different repositories. Here you can also create an account, and if you're working on a project with Google and you need access to one of the repos on here, well, we can certainly get you set up to do that. And we do that all the time. So you've probably used this already if you've been working on a project with us. And so those are just the two gerrit sites. Any questions on gerrit stuff so far? No? So now we'll break into Portage, and I know this is a very popular topic. Chrome OS, of course, uses Portage for all building. So what is Portage? Portage is a package management system used by Gen 2 Linux and by Chromium OS. It's basically a way of building a whole bunch of stuff relatively easily. And it's and in that way, it kind of works like a Debian package manager, only instead of that, you're actually using the source to build everything instead of pulling down from a binary that's been built by somebody you've never met. We can still pull binaries down, which we'll talk about in a little bit with pre-builts, but the goal of Portage is, in general, just to be able to build a lot of stuff from source. What is Portage made of, you might ask? It's made of a Portage tree, which has a whole bunch of ebuilds in it. And the main tool you'll use here is emerge. Who's used emerge? Has anybody actually run their own Gen 2 distribution? Yes, yes, we have winners in the back. You deserve extra cookies. It's really a good experience. If you haven't done it and you're really into Linux and you like things to take a while, Gen 2 is very fun. It teaches you a lot about what the underpinnings of the way the Chrome OS build system works. So it's a helpful learning exercise in that way. Okay, so we said Portage is made up of a whole lot of things called ebuilds. What's an ebuild? It's basically just a bash script. So these do basically defines everything that it needs to know about the package to be able to build and install it. So it will say, where do I get the source? How do I build the source? What options do I need to put into it? And then how do I install it? So basically every single package in Chrome OS has an e-build for it somewhere in the Portage tree. The Portage tree is basically a whole bunch of e-builds. It also includes some other pieces like e-classes, which we'll talk about in a second. But the basic idea is that this is where you find all the bits and pieces. So if you wanted to add a new package to Chrome OS, what would you have to create? An e-build, yes. Very good. So the idea is that if you wanted to add a new package, you would add a new e-build. Chances are, if you're adding a package that exists somewhere else, the e-build probably already exists somewhere, and may just need to move it around. But that's basically what e-builds are. A virtual basically it is the same as an e-build, except it's a kind of like a pointer. So you would have a virtual if you had a package that, say, I wanted to have what would be a good example? A firmware, yes, but you didn't know which kind of pieces which particular type of firmware you might want. So you would make a virtual called some firmware, Chrome OS Firmware, and then that would actually point to a particular e-build that actually contains the pieces you want. That way you can just build one thing and have it always bring in what's needed for a particular board. Okay? Any questions on e-builds? How is it different from a make? So at a low level, it will actually end up doing that depending on the package. It could actually call make. The difference here is that this is all kind of put together in like a giant tree structure, so you can have a whole bunch of different makes potentially going on in parallel. It's kind of like a giant build system is really. But underneath it can use make. I think make would be difficult to build all of Chrome OS all at once. I haven't seen it tried. Nothing? Okay. I don't have a better answer for that. I have used make before, but not at this scale. But maybe it would be. But this allows us to do some things that I think would be difficult to do with make, like having pre-builts and things like that, which we'll talk about. So what's an e-class? We talked about e-builds. The other piece that you might find in a Portage overlay is an e-class. And these are basically kind of like header files almost. So you can have a generic e-class that might have some functions in it that might be useful for building different types of packages. And then you could include those in some e-build and then have access to those functions. So you see that an example of this would be the cross-binary e-class, which we use for managing files that we store on BCS, which we'll talk about in a little bit. But basically, if you see something that's an e-class, don't be afraid of it. It's just like a subset of an e-build. And so emerge, we mentioned this already once. Emerge is probably the command you'll end up using the most. This is basically, I want to make for a particular package. And so if you run, say, emerge vim, it will go out and try to find the sources for that particular package. It'll find the e-build for vim, which will then find the sources for the package. It will take them and build them, and it will install it in the target. So in a Chromium OS build environment, we actually basically make these overriding functions for it. So instead of just emerge, you would use emerge dash your board name. And this basically says, I would like to build this package and put it in the file system for my particular target. That includes doing things like cross-compilation and all that stuff. It's all kind of hidden by the Portage magic. And so what this would do in this case, if I was building for, say, ARM generic, I would do emerge ARM generic vim, and that would basically take a vim binary and ultimately have it end up in the file system on my device. Another common option for this is unmerge. If you wanted to remove a binary or from a package that you have previously emerged, you do dash dash unmerge. It'll make it go away. And that's pretty much it. So this is somewhat like the Gentoo equivalent of apt-get, similar with Chrome OS. Basically, I want to find this package and have it. And of course, whenever you're working on a package, you will also get to use this a lot to continually do builds and all that. Another handy command whenever working with Portage is equerry. So this will allow you to find out all sorts of stuff about various e-builds and various files that exist in the source that you're working with. So you could do things like, if I had a file, like a C file, and I didn't know where it came from, I could do equerry b file, or belongs, and it will actually go and try to find which package contains that. Okay? You can also use this to find out dependency graphs and things like that. And I think Dave will show an example of this later during his segment. And you can kind of like dig around in where the Portage tree is to see where everything is and who's dependent on what. Because whenever you emerge, say, something like Vim, you don't just get Vim. You need all the dependencies that that has for it, right? Because there's 100 other things before you can actually get to the point that you have a text editor, okay? So any questions on these? Has anybody used these before? No? Good. People in the back have used it a lot. Okay. So we've talked a little bit about Portage trees and what is Portage. Now we can talk about what is an overlay. So any board we have has its own overlay, and an overlay is basically a partial Portage tree. So what this allows us to do is to have unique e-builds for a particular build setup. Okay, so if I wanted to have a specialized firmware per se, I would have a overlay that contains an e-build that would have this firmware e-build in it. Okay, and so that's pretty much it. And we'll show some examples of that later on here. So if you look at the way that the Chrome OS Portage tree is kind of structured, at the very bottom we have source third-party Portage stable. This is kind of like the generic Portage set of e-builds. So this is where, if you were to emerge Vim, it would probably come from here, because there's nothing customized for Chrome OS for it. This is kind of just where you get all your basic Linux packages. If you have something that is more Chromium OS specific, then it will end up in this overlay. This is where we, in the Chromium OS overlay, this is where we have our own custom packages. And of course, as you get into more Chrome OS specific setups where we have private stuff, you'll have the Chrome OS overlay for things that we can't have in the Chromium OS overlay. And then as we go up the stack, we get into the point where we have the partner overlay. So this is also private stuff. This is pieces that you would still get if you're registered on any of the private projects. But so things like Chrome OS MRC if you're working with an Intel platform. And then the last two on the very top here are the board-specific ones. And this is how, basically, if you made a new board and you wanted to have different pieces go into it, where they would go. And it's split into two pieces. There is source overlay in your board name, and then there's the private overlays, overlay board private. So the overlay board is going to be public, and the private one is obviously private, not shared. It would go on the which gerrit? Gerrit int. Very good. Okay. And so basically, our goal is to have that be kind of as thin as possible, because we want to be a good open source project and have a user be able to build things. So we try to put as much as we can into overlay board, but there are always pieces that have to go into the private. So typically things like some OEM customization that are not shareable, in cases where we have licensing conflicts, so say your platform has to have certain binaries to make the firmware, we would have to hide those in there. Okay, any questions on the overlay structure? No? Okay, so this is a good topic, cross-work-on. How many people have used cross-work-on? Fewer, that's, okay, there are some more. So cross-work-on is very important, because if you start trying to make the changes to Chrome OS and you don't use cross-work-on, you're going to have a very frustrating time actually testing them. So who has tried to make a change to Chrome OS and not cross-worked on and run into the, why isn't my change going into effect? Okay, pretty much everybody does. It took me a while to get it the first time, but hopefully now that you have this slide, you'll now know and you won't get stuck. So basically, what this will do is it will tell Portage that I want to always build from source on this package, and I want to use the source that I have locally for this package. Okay? And what that means is whenever you normally build something using Portage, you end up using the stable version of that package, which isn't what you have in your local sources, and it may not even be built locally for you. It may be pulled down from a binary repository we have to speed things up for you. So this will force everything into place. Yes?
So do you have a good way to generate a branch using Git for the build from source from the stable release? So basically generate a Git branch from whatever $1 hash the stable releases was built at.
So the question is there a easy way to get a Git branch from the stable release, or the stable version that the eBuild's currently pointing at?
Yes.
So in theory, that should always be what it is, what master is. So in theory, it should always be pointing to mmaster if the builders are all working. Because what happens is you end up, you submit your change, it goes into the Git repository, the builder will uprev the eBuild, and then the new stable is what the current top of head should be. So as long as you're not on a local branch or something you've made, it should be that branch. There's probably a better git foo way of pulling that out because it's in the eBuild, but I don't have an easier way of doing it. You could also just look at the eBuild and find the hash. Okay. In addition to so the cross work on command is basically, we have start and stop. So start will allow you to start working on it. That means you'll always build the sources. Stop means I'm done, just give me the stable versions. And then there's also a couple other commands, info, list, and list all, that will tell you what you're actually cross worked on so you can kind of see the state of your development environment. So any questions on cross work on so far? Huh? Okay. So if you're actually working on eBuilds, you might ask yourself, what is a cross work on package? It's basically anything that inherits the cross work on eClass. And typically, if you look in your Portage tree and you see a eBuild that has a -9999, that probably means it's cross work on, and you'll probably want to cross work on it. Note that there are some that are not cross work onable. So packages that are not really involved in Chrome OS that you might not normally be changing won't have a cross work on aspect to them. You'd have to manually uprev them to make sure that the stable version is what you've changed. But most of the stuff you'd work on is cross work onable, and you'll see that in most cases. And so, like I said, kind of there, getting ahead of myself, for non-cross work on packages, you would actually need to uprev them. So, and that basically involves making a copy of a symlink or making a copy of the eBuild that actually has a version number that's higher than it was before. So can anybody tell me why it's important to do this?
So that it gets upgraded.
So that you actually build the new one, right?
Yep.
Right. So basically what you're doing here is you're saying, I want the stable one to be the new version, and then it will effectively use any changes you put into it. And this is also the case if you're making changes to the eBuild itself, right? So the question is there a test before the uprev happens? Yeah, so there's actually multiple stages of builders, and at a minimum it will guarantee that the build succeeded before the uprev happens. So it will be caught by one of our Paladin builders, essentially. That doesn't mean functional testing has all been done on it, but it will at least build. We strive to make sure that it doesn't break in other ways, but okay. No other questions? Okay, so we also mentioned that in addition to, even though Portage is really designed for building from source, and we obviously build from source all the time with the builders, to save you a little bit of time, we have pre-builds. Because building Chrome itself will actually take an hour on a machine with 16 cores. It takes a long time. It's really slow. But luckily, since we have all these builders doing these continuous builds in the background, we can provide a binary of this that you'll be able to download much quicker. Okay? And so for a variety of packages, by default, you'll always be downloading them. And in some cases, you kind of need to. So for example, if you're working on Intel stuff, the Chrome OS MRC package isn't something that we have available in source. So if you try to just build it, you would fail saying, oh, I can't get access to this Git repository, right? But you can use the pre-built to actually pull it down. And that way you can continuously successfully build your firmware even though you're missing some of the sources. Okay? And like I said previously, the 9999 builds are always built locally. That's kind of implicit to the Chrome OS build system. And whenever you're setting up a new overlay, if you were to do that, the Google Storage ACL Bodo file is where the ACLs for this come. So you basically have to have access to a private overlay to kind of get these pre-builts. So that also implies if your project is very early on, like say we're bringing up a new chipset, there may not be pre-builts for the first month or so until we get around to making a builder for it and setting up these ACLs and all this fun stuff. But we normally try to get that going pretty quickly because it's very impactful for if you're building test images. Okay. So that's pretty much it for the basic Portage the gerrit stuff. Any other questions on any of that before we start breaking into firmware branches? No? Okay. So, Chrome OS branches all the time. We actually branch every 6 weeks for stable releases. So whenever you get a Chromebook, every 6 weeks you'll basically get a new OS version for it. This also covers Chrome the browser. So if you're using Chrome the browser on any other platform, that also is continuously updating. And so we kind of follow the same cycle. So basically every 6 weeks we will cut a new branch. And then that branch will be driven as at that point, the branch will only get changes that are considered bug fixes and not new features, whereas top of tree, we can kind of throw whatever we want on it. And the important things to note here are that whenever we're shipping a new device, the FSI, the final shipping image for that device, will come off of one of these R branches because we want it to be stable when the user gets it. And the other implication here is that because it's so fast, it's quite likely that by the time a given customer gets the device, it may get an immediate auto update to the next version. And so this lets us be fairly nimble, so we can get fixes in all the way up till the last second as we're working on them. So that's kind of like the generic Chrome branching story, but for firmware we do things a little bit differently, because firmware we hope to never have to change it all that much. So at some point in time off of TOT, we will take a firmware branch and just create it. This is generally done for the reference board, and this is kind of like the goal shape that we would like to have, where we branch a reference board branch, use that to stabilize the firmware, and then as we start making additional devices off of that, they will get their own branches that come from that branch. And this allows us to basically have a very stable firmware and allows us to do things like basically whatever is necessary to make it work with less concern for scalability of the code at that point. We still want to make sure that everything that goes in is as clean as possible, but this allows us to be more flexible on that point. Whereas everything that goes into TOT, we always have to make sure it's very clean because it's going to be used for everybody in the future. And in this case, we have a firmware Ramby 5216 branch that actually exists if you're working on Ramby. And at some point, we will branch other firmwares off of that as we go. And the same applies for other platforms. We'll obviously get other branches. So any questions on the basic branching strategies? No? Oh, yes.
So the intent with the firmware branches is that they are the type of branch you get when you're trying to quickly bring up and ship a product, and the changes on that branch would go through some form of cleanup and or cherry picking to get back onto top of tree, but not directly be merged?
So the question is the firmware branch meant for a quick bring up where the changes that go into it might have to be cleaned up before they go on top of tree? And the answer is somewhat yes. The main reason that I see that we have the firmware branches is such that we need something that is always going to work and always going to be stable, and we can't continually change TOT and necessarily risk breaking a 3-year-old product at the firmware level. And so the main reason is primarily stability. It is still good to land things in TOT and then cherry pick them onto the branch if possible. That's my preferred method. However, if you're working on a product that's not the reference, that might be something that doesn't even have support in top of tree, because for example, even though the Rambi kind of exists on both, the products that are based on it will never necessarily exist in TOT. They don't even have a build spec. And so for things that apply to everything, it's good to have them landed on TOT and cherry pick over. If you can't do that, you can land them on the branch, and that's fine. And board-specific stuff may only ever live in the branch. So I'm not sure if I've entirely answered your question or kind of mangled it, but.
I think that answered the question exactly. It sounds like that was the reverse of what I thought you were suggesting. This isn't for early, this is as much for late of keeping it stable for long-term.
Yes, exactly.
Okay.
So very good. Any other questions on branches? Okay. So this is kind of a big diagram, and we'll dig down to this in the next coming slides, but this is basically the life of a firmware image. So you might ask yourself, we have this firmware branch, well, how does that actually end up in a production image on a user's machine? How does it all go through the system? And indeed, there are quite a few steps for it. To start with, we'll basically have the firmware branch fed into a firmware builder that goes to the test team. They'll upload it to a BCS server, and at that point, we can then ingest it on the top of tree, put it into a shell script that will install it on a device, and then actually send it out to the devices. So let's kind of step through these a little bit closer. So the first thing that we want to look at is the firmware branch builder. So assuming we've put all the stuff we need to into the branch, and we're ready to build a firmware, all we need to do is have the builder run and do its thing. So what the builder will basically do is run emerge, the name of the board, Chrome OS Firmware. This is actually a virtual that will pull in all the other pieces underneath of it to make a firmware binary, or actually a set of firmware binaries, including both the firmware for the AP and the EC, and throw it in a firmware from source.tar.bz2. So if you've looked on the builder artifacts or on CPFE, which we'll talk about in a little bit, you may have seen a file called firmware from source.tbz2. This ebuild is what generates it, and this is where you would normally get it. So after we get the firmware out of the firmware branch builder, we want to make sure that the firmware is good, right? We don't want to send out a firmware that's going to go and, say, brick a machine, especially when we're sending auto updates to thousands and thousands of units potentially after we go to production. So the test team will take these images and run them through a variety of tests to make sure they pass muster, including FAFT, which we'll talk in a little bit, fully automated firmware testing. And after that's been approved and everything is cool with the firmware, then we could take the firmware and upload it to the binary components server. And at this point, basically, we've kind of whittled down everything that's in that file to just an image.bin and an ec.bin. And this is the image.bin is literally what goes directly on the SPI, and the EC is literally what goes directly into the EC. Okay? And this is all the work that's really done on the firmware branch. After this, the firmware branch is kind of done once it's on BCS, and we don't really use it for anything else. The firmware branch never really builds a full OS. It doesn't need to. I guess it could, but it really only needs to build the firmware pieces. And then say we've gotten it up there on BCS, and we want to actually push it out to a real OS image. So since it's on BCS, we can reference it in the Chrome OS Firmware Board ebuild. So this normally exists in the private overlay. This is basically going to generate what we would call a shell ball. It's a bash script that has the firmware and EC embedded into it, and it has the bits and pieces that know how to write it to your device. Okay? So this particular ebuild will take the pieces from BCS and put them in that script and put it in the OS image for you. So assuming we've made that change, we're now referencing BCS in our ebuild, and we move on to the builder that will give us our OS image. In this case, let's just say it's a canary builder. This is kind of like the I build TOT every few hours builder. And it will basically generate a new OS image that contains this firmware. And then after it's done building it, another step that we don't really go into too much detail often is the signer. It is actually a separate machine somewhere. So the Canary builder generates an OS image. The signer will take that image, sign it with keys that are Google-specific keys, in which we'll talk about some of those keys in a minute. And in part of that process, it will actually take the firmware installer and sign the firmware images in it. So in this case, for many projects early on, we'll sign them with pre-MP keys, and later on we'll sign them with MP keys, which we'll talk about what those kind of mean. But basically, this is now a Google-signed official recovery image, and we consider it a trusted device at that point. So after the signer's done with it, what do we do next? There's a couple different places it can go. So for automatic updates, if the system is set up for AUs for this particular device, it will automatically go out over the internet and start hitting devices. Those will get updated, and their RW firmware and RWEC will now be the new one. Also, since you're working closely with us, you probably have access to the CPFE site, which we'll show some screenshots of in a little bit, and you can actually download the recovery images directly from there. And one other thing to note here is that the release branches really do the same thing. So if I wanted to update the firmware on a release branch, all I have to do is go in and make the same CL that I do on TOT, and then it will do the same process. And instead of being a canary builder, it would end up being a beta builder or a release builder or a stable builder. So any questions on this? I know it's kind of like a long process, but it seems kind of complicated whenever you look at it from the outside, but it really makes sense if we want to have a stable firmware and then we want to get it into an OS image. This is kind of the flow. Okay, so we mentioned some keys before. We said pre-MP and MP keys. So let's talk about those. So there's basically kind of three classes of keys that we're using with Chrome OS. The first you've probably used is basically the unsigned version, which is a dev key. This is kind of the you could do whatever you want with it key, no limitations, it's all public, and this is kind of what you get if you just built an image out of the box. Pre-MP keys are the keys that we kind of generate as almost temporary keys. They're really just pre-MP. And we use those to sign things for early hardware so that we can test the signing process and make sure everything is going to work and that we're okay with it. And this is also kind of required before we start sending out automatic updates for systems, and this should be in place by the DVT phase of any given project. And the final set of keys are MP keys, and there could be multiple versions of these over time, are the official mass production keys that are locked in a vault somewhere and kept very secure, and I didn't put the elves part, but that's pretty good. And basically this is kind of like, this is what you would get if you buy a device at a Walmart or Best Buy, wherever you go to get your Chromebooks. It will be an MP signed image. You would never see pre-MP or dev on these unless somebody took the device and hacked it. And these are basically all the same type of keys. They're really just the names we give them, dev, pre-MP, and MP. And so basically, you kind of have to have your firmware and your OS image aligned such that it will boot. And that was kind of talked about a little bit with the verified boot stuff we talked about earlier today. But it'll come in practically. So if you wanted to say, get a device on automatic updates, you would want to have it have a firmware that is appropriately signed. So basically what you would do is you would pull down a recovery image from CPFE, since you guys should all have access to that, and install it on the device. Part of doing the recovery image will actually end up rekeying the device because it will end up rewriting your firmware with the signed firmware that it contains. And so this will allow you to get a device to the point where it will automatically update. And this is kind of important whenever you're working with a lot of prototype devices because they may come with some other junk firmware, they might come unsigned, who knows. But you can use the recovery image to kind of get the device into a known good state, and then it will update itself to the latest OS image that we're currently pushing. And another piece that's often useful is if you had been doing, say, firmware development on a device, there's a good chance you've wiped your hardware ID. And if you need to put one back in, this is a small set of commands to do it. I know earlier we had a slide that said there's a set GBB script. I know that's in some images, but it's not in all. So if you're using just like a normal image, you can always do this. And basically all this is saying is I read the image out, I set this hardware ID value, and I put the image back into the SPI. And the hardware ID, I would just probably take one from another device that you know is good and go with it. So there's actually a whole lot more to the hardware IDs. It's more of a factory-specific discussion. These are what we use to, it kind of is almost like a hash of the hardware on the device that we use to make sure that we're using the components we expect and that we can always go back later and see what components are in the device. But they're also used for the auto-update system, so it's important to get that set right. So any questions on this stuff so far? Keys and signing? So now let's do a little bit on code reviews. So I know several of you have used Gerrit before and put things up on Gerrit, so we'll just step through the basic process right here. You've probably done this, so maybe it's not a big deal, but the first thing that happens is the author does a repo upload step that actually generates the CL on Gerrit. We have a reviewer somewhere who is going to provide some feedback. The author will then look at the feedback, make some changes, fix things up, make it look a little bit shinier, repo upload again. Then let's say this time it was better. The reviewer will go ahead and +2 approve it. And it's basically just like click a box on the website, very simple. Normally this would be someone at Google approving the code. Depending on how we're working, you may have the rights to do that on a certain branch. But generally this would be somebody at Google reviewing the code to make sure it makes sense to put in. And then the author will say, okay, I've verified that this works. I've done my test, whatever I put in my little test equals field. And it's ready to go in. I'm ready. And then after that, it will go into the commit queue. So this is actually a picture of the public waterfall. Anybody can see this. And what will happen is every so often, there's a set of builders that run sanity builds, which basically does the protection step that she was mentioning to make sure that we don't uprev into some junk. They'll do builds of everything, and if they all pass, your CL will then go into the Git repository, the uprevs will be done, and you will have succeeded in making a change. So there are some guidelines to this and things that will help if you're making changes. It's good to keep your CLs kind of as small as possible. The smaller they are, the easier they are to review and get in. It's good to separate your board-specific and global changes. So let's say I'm adding some new feature to a board that requires me changing some piece of a driver somewhere in core boot. I would probably want to have the piece that I change for the driver in core boot separated from the piece of the board that I actually enabled it, such that we can work with them independently. And it also makes it easier just to review them separately. It's also important to, if there is a bug open for it, reference the bug in the CL. Whenever you upload, it will complain if you don't have a bug equals line. You can say bug equals none, but it's better to actually have a bug there because that kind of gives context to the CL and makes it easier for people to go back and look at what it was and why you did it. And all that. And it's also very important to add a reviewer. Some of the repositories are watched like hawks by people, others may not be. And if you don't add someone, it's a possibility that it will just kind of sit there and no one will do anything about it. If you add people, generally people are glad to look at code and help review it and get things moving along. So, and if you don't know who the reviewer is, then you can go ahead and look. The git blame command here will basically tell you who's made all the changes to each line in a file. You can also look at git log in a particular area and see who's made the most commits to something. And generally those people will either be able to help you review it or know who will and will gladly bring them in. Okay? Make sense? Any questions on code reviews or any of this stuff? Yes? So the question is, we mentioned bugs. Is there an infrastructure for tracking the bugs? If you put a bug equals chromium : the bug number, theoretically the bug droid will actually, after your change lands, go and update the bug with the commit message from your change. So the bugs will actually get notified whenever your change lands, which is another good reason to do it. Same thing with the internal tracker. It would just be Chrome OS -partner instead of Chromium for the bug. And if you look at any of the CLs, they'll have it. The syntax is very straightforward. It's literally capital BUG equals Chromium : and then a number. And the number is just what comes out of the tracker in the URL. Okay? And with this,